So welcome to third week of lectures. In this lecture today, we will be discussing Bloch equations. So Bloch equations, what are Bloch equations? Let us see. So basically it describes how magnetization moves in time when RF field is applied. When there is no RF field, how magnetization precesses about the B0 and how relaxation perturbs the motion of magnetization. So it tries to explain the motion of magnetization in different conditions, right? So by now we are all familiar with the terms when we are saying B0, B1, RF field, which is same as B1 basically, and what is B effective, what is M naught, what is MZ, what is MXY, MX or MY, right? What is delta B naught, what is offset, etc. Right? All of these terms are familiar, and broadly we know that if this is our magnetization to start with, and if this is my B1, it will try to precess about this B1, right? Like this. And if my B1 is along x-axis, it will go towards minus y-axis. So this is what we have learned, and this is in the case of no delta B naught, that is on resonance condition, right? So now let us see how all of these motions are actually explained by in the vector diagram, how this is explained by Bloch formalism, right? So we are well aware of the fact that magnetization precesses about the effective field, and that is given by dm by dt is equal to m cross gamma B effective, right? This we have already seen. So in other words, if I want to draw it, if this is my B effective and this is my M, it will precess about this, right? It will precess about B effective, and it's given by this equation over here. Now let us decompose the vector M and B effective in along the x, y, and z axis. What are the different components? Let us look at the components of M. So M can be decomposed into mx I cap, my j cap, mz k cap. So where mx is the component of M along, or projection of M along x-axis, projection of M along y-axis, projection of M along z-axis, and I, j, and k are unit vectors along x, y, and z-axis, right? This is all traditional vector algebra. Similarly, B effective, we have learned that B effective can be broken into x, y, and z components, something like this: B1 cos phi I cap, where phi is this angle. So if my B1 is this angle is phi, right? This with respect to x-axis. Whatever angle is there between x and B1, this is called as phase factor. So B1 cos phi I cap plus B1 sin phi j cap, and B effective is composed of delta B naught also, considering that there is a delta omega present. That means there is some offset present. So this is delta B naught, which is along z axis, so it will be k cap. So now dm by dt can then be written as dmx by dt plus I cap dmy by dt j cap plus dmz by dt k cap, right? Now all of this is m cross gamma b. So my m is written as mx I my j mz k cross product gamma this value over here, right? So I'm not going to repeat that. Okay, now what we can do is we can write this cross product as, so we can solve this cross product as following determinant, right? This you must have learned in your vector algebra. So how do you do that? So you write ijk and the corresponding coefficients mx my mz, and then gamma b1 cos phi can be written as minus omega 1 cos phi. This becomes gamma into b1 becomes minus omega 1 sin phi, and this is delta b naught. So this becomes offset, right? So delta b naught into gamma becomes offset, which is written as capital omega. Now if you solve this, this can be written as I, so you take this and then you multiply this minus this, right? So I cap offset my minus, and then this becomes plus, so you have omega 1 and this will be minus actually, yeah. So omega 1 sin phi mz minus the z component, j component, sorry. So this will be written as minus j mx into this minus this into this. Okay, so this becomes minus offset mx this will be plus omega 1 cos phi mz, and then plus k. This becomes, so you take this and then subtract this, minus omega 1 sin phi mx plus omega 1 cos phi my. So now you can compare the coefficients of I, j and k, and thus you can write dmx by dt as minus offset my plus omega 1 sin phi mz, then dmy by dt. Now this negative sign can go inside, and then you compare the coefficients of j cap. So this becomes offset mx minus omega 1 cos phi mz, and the last part is dmz by dt, which is now equal to minus omega 1 sin phi mx plus omega 1 cos phi my. Okay, so now Bloch actually also factored the relaxation part into these equations. So what is relaxation part? So he proposed that the transverse magnetization decays with a rate of R2 following first order kinetics. So what is first order kinetics? So let us look at it quickly. So if a reaction is going from A to B with a rate constant of K, so the rate dA by dt is defined by minus K times A, right? So very similar to this, so Bloch defined that dmx by dt should decrease by a rate, transverse relaxation rate, as minus R2 mx. And similarly, he also said that dmy can be written as, in a very similar way, minus R2 my, where R2 is nothing but inverse of transverse relaxation time. So this is transverse relaxation rate and transverse relaxation time. Okay. And then the Z magnetization was actually proposed to be written as recovery. So instead of decay, it is called as recovery of the MZ magnetization. So that's why there is no negative sign here. It's a plus positive sign with longitudinal relaxation rate, because this is where the populations are getting back to equilibrium, to thermal equilibrium, and this is how far it has recovered from M naught is. So this rate is proportional to how far it is recovered from M naught, right? Okay. So and the positive sign is because it is recovery, right? So now these three parts can be directly incorporated into these equations over here. So what we can do is we can directly write this as, let me write it with a different color. So minus R2 mx, and this will be minus R2 my, and this will be plus R1 m0 minus mz, right? So now this whole thing can be written in a more presentable way, I would say, or some books prefer this way and some books prefer in a way where it is written in terms of matrix. So the whole equation, this set of equations are called as Bloch equations. And let us try to see how does it look when you write it in matrix form, so it makes more sense there. So what you do is you write d by dt of mx, my, mz. Now this whole thing is equal to so this will be your so let me just go back there. So you will write first the mx part, followed by my part, then the mz part, right? So what I'll do is I will write here minus R2, which is the mx coefficient, followed by my coefficient, which is negative of offset, followed by mz coefficient, which is omega 1 sine phi, right? And then you will have, because you have taken mx, my, mz out, so it comes here, so it doesn't mix with this. Now similarly for dmy by dt, again first you will write mx part, which is offset, followed by my part, which is negative R2, followed by mz part, which is minus omega 1 cos phi. Now for mz, this is minus omega 1 sine phi, omega 1 cos phi, and here it is this will be R1 minus R1. Okay, plus there is R1 because there was M0 minus MZ, so this will be M0 over here. So this is called as another form of writing the same thing. These are called as Bloch equations. Now if you see, this has a effect of offset. So this is the effect of offset onto the motion of mx, my, mz. The relaxation part, which is transverse and longitudinal both, and then the effect of the pulse, that is the RF pulse or B1 field or omega 1. So anything which basically perturbs mx, my, mz is incorporated here in the Bloch equation. So these are phenomenological equations which completely describe the motion of mx, my, mz, at least in certain cases, right? Okay, so now let us see what happens when so let us look at the effect of motion as we can calculate using Bloch equation. Let us first see a case where we have just switched off the RF pulse. Okay, so let us consider a case what happens to the magnetization if we turn off RF field. So that means what we have done is we have applied RF field and then we have turned it off. So the magnetization is now in transverse plane, and then you switch off the RF field. So if you switch off RF field in above situation, any term which is containing omega 1 will go to 0, and because there is no Z magnetization, so we will not consider the 3x3 matrix. Instead we will consider only 2x2 matrix of mx and my, right? So then what do we have here? So what we can do is we can write dmx by dt is equal to minus r2 mx and minus offset my. Similarly, dmy by dt is written as offset mx and minus r2 my. Right? So in practice, both the components are detected simultaneously. We'll discuss that case, how we detect both the components, and signal can be thought of as a complex signal. So if we consider that this so to ease out the mathematics, what we do is we consider that this is the real part of the signal and this is the imaginary part of the signal, and then both of them can be the total signal can be considered as the complex signal, complex NMR signal, because essentially when mx is going back to z-axis or my is going back to z-axis, it is inducing current in the coil, and that is detected as the signal. So the motion of mx is generating a signal and motion of my is generating a signal, and part of the signal is supposed as real signal and this is supposed as imaginary signal, and then you say that the total signal is the complex signal, right? Okay, so then we can write something like this, that m plus is a linear combination of mx and my in complex form, right? So this is just to keep mx and my components separate while we consider that the total signal is composed of mx and my, right? But we are still not mixing mx and my. So that's why this complex treatment is given to this. Okay, so now if we do that, we can write dm plus by dt as dmx by dt plus I dmy by dt, right? So this is the total complex signal. Okay, now if you substitute these values into this equation and separate out the variables, what we can get is, we can get I offset minus R2. I'm skipping some mathematics, but this is all I have done is put in these values for dmx by dt here and put in these values and then separate out the variables. This becomes mx plus iy my. Okay, and this is dm plus by dt. Okay, so that means this can also be replaced with m plus. So what I've got here is I offset minus R2, and then this becomes m plus. Now if you integrate this equation, what do you get? So let's go to next page. Now if you integrate the equation, let me write that equation again. So dm plus by m plus now. So I'm separating the variables. R2 dt, right? Now this can be easily integrated. So what I have got is natural log m plus is equal to I offset minus R2 times t plus, you can have a constant which can either be written as k or negative or the logarithm, natural logarithm of m0 t plus, sorry, right? So magnetization at m plus at t equal to 0. Now again what you can do is you can bring this down over here, and then you can write m plus divided by m plus of 0 at t equal to 0 can be written as exponential of I capital omega minus R2 into t. Now this can further be separated as e I omega t into e minus t R2. Now this is the oscillation part of NMR signal. So this overall is the NMR signal, right? So this is oscillation part, and this is the decay part or the relaxation part. So as we have learned that the signal is oscillating with frequency with offset omega, and signal is decaying with this rate R2, right? So now if you now break this complex into again the real part and the imaginary part, so the real part of the signal can be written as cos of omega t into e to the power minus t R2, and the imaginary part of the signal can be written as sine of omega t into e to the power minus t R2. Okay, so now this last thing, how to plot this, and if you simply plot this, this will look something like this. This is a cosine wave, so it will start from here with a decaying nature, so it will look something like this. So if you map the surface of this cosine wave on top, this is an exponential decaying curve, and this curve is nothing but this, and the cosine wave is this, right? Okay. And the wavelength here is given by lambda, let's say, is given by 2 pi by offset, and this gives you the rate R2. Now similarly, the imaginary part of the signal can also be plotted as a decaying sine wave now. So sine wave, so it's starting from here. So again, if you see that this is the maxima of the trough actually map out the exponential decay part, and this is the sine part. So again, the wavelength, so this is not the correct picture of wavelength. Let me, so wavelength should go from here to here, right? So this will be our lambda. Similarly here, the wavelength will go from here to here, and this portion is called as lambda, which is given by 2 pi by omega, 2 pi by capital omega, and this gives you the R2. So whenever you're recording any NMR spectrum, all you need is an information about what is the offset of that particular proton or that particular nuclei, and what is the relaxation rate by which it is decaying, right? So both the informations are available from this graph. If there is only a single proton, let's say if you have just the water as the sample, so only one type of proton, so you will get only one type of frequency from this, and you will get a very nicely decaying cosine or a decaying sine wave, right? So in next class we will see how actually we get a friendly looking NMR spectrum from this type of a curve, and what happens when you have multiple of protons in there. So instead of one type of proton, let's say if you have 3 types of proton, how does this spectrum looks like, and then what happens to the spectrum after you do further processing. So all of that will be covered in next class. Thank you very much for joining.